Yeah, if you want, I can go ahead and share already. Then it's set up to start.
Hi, Jan, how are you? This is Tolga.
Hi. Nice to meet you.
Nice to meet you too. Let's wait for a few more minutes. We have some time anyway.
Hi, Samet.
Okay, Jan, if you're good to go, we can start, I guess. Thank you very much for accepting to give this talk. It's a great pleasure to have you here. And the stage is yours. So just go ahead. Thank you very much again.
Yeah, thank you for having me. And sure, then let me start. So you can all hear me all right and see the screen, can't you?
All good.
Okay, nice. Yeah, so it's really a pleasure to show some of our recent work. And yeah, today I want to talk about how we try to track down new and so far unknown isolated neutron stars using the SRG eROSITA all-sky survey and XMM-Newton. Oops. Oh, wait. I'm in the wrong window. I'm sorry. Here we go. Yeah, so this talk is roughly divided into 3 parts. So I want to start with a rather general introduction to the phenomenology and the properties of isolated neutron stars, and then a bit focusing on the rather elusive class of the so-called X-random isolated neutron stars. Then, of course, describe how we search for new neutron stars in the eROSITA all-sky survey and XMM-Newton, and then finish with some of the nice results that we have already obtained from the dedicated follow-up observations. But let's start at the beginning. So as most of you probably know, the evolution of a star is heavily dependent on its mass. And if you look at stars with within a mass range of about 8 to 20 solar masses, they will roughly follow the lower track here below, and their life in a supernova explosion where the stellar core collapses into a neutron star. These objects are rather extreme, as you probably also know. As such, this can already be seen if we just take the canonical neutron star that is often assumed to squeeze about 1.4 times the mass of the Sun within a radius of about 12 kilometers, which directly implies that the average matter density is on the same level as that of an atomic nucleus. Consequently, one of the most sought after results, or the most important studies that are done if we look at neutron stars, is to constrain the properties and the underlying physical mechanisms of the matter under these extreme densities, which is all more or less summed up in the goal to constrain the nuclear equation of state, namely to relate the thermodynamical properties like pressure, density, and temperature to each other. While the equation of state definitely already is not enough reason to study those sources, it is also important to note that they are among the strongest magnets in the universe. So we can also constrain quantum electrodynamics in a rather extreme laboratory. And obviously, which are probably most known for, is their fast and rather stable spin periods, with the bulk of the population having periods of between 1 millisecond and about 100 seconds. So if we want to sum it all up, these objects give us rather conditions that are unreproducible in earthly laboratories, and then are therefore rather unique cosmic laboratories that we should definitely have a look at. However, if we want to observe, to use those laboratories, we need to observe them in one way or another. And while recently, a new observing window has opened with gravitational wave astronomy, in this talk we will try to keep our object of interest, unbroken, so not merging together. And therefore, we will refine ourselves to good old electromagnetic radiation. And in this regard, one can perhaps distinguish between three major emission processes in these sources. The first could, of course, be accretion from a nearby companion, which is, for example, illustrated in this nice artist impression here. These objects, known as X-ray binaries, are quite cool because, in principle, they directly allow to infer dynamic mass range mass measurements of the neutron star, which could constrain the equation of state. However, in this talk, we are not looking at neutron stars that are evolving in a binary system, but more at the isolated neutron star class, meaning that they, at least in their emission properties or maybe in their overall evolution, are not affected by a binary companion. But also here, it's maybe important to note that accretion could play a role. For example, if they would be traveling slow enough, there was the idea that they could accrete from the interstellar medium. Or maybe if you have a look at supernova models that predict that part of the ejected envelope could fall back towards the neutron star, forming a so-called fallback disk, that then could also lead to electromagnetic radiation due to accreting matter. What is also important to consider if we look at neutron stars is the so-called magnetospheric emission. In this regard, it is maybe a good idea to have a look first at how we, at least the first order, oftentimes approach the magnetic field structure of these sources. And as you can see in this nice artist impression here from Blaskowitz et al., this is usually often taken to be in a dipolar magnetic field with two magnetic poles here. In the magnetosphere now, it is the case that due to the fact that oftentimes the magnetic field axis and the rotational axis are not aligned, so-called charge-free gaps can form where few charged particles can be accelerated or pair production can take place, leading to the fact that if you accelerate those charged particles, synchrotron or curvature radiation is emitted. And as is nicely illustrated here in this artist impression or in this figure, this radiation is oftentimes rather focused, going away in this regard. It is also important to note that this radiation can be seen from radio to gamma rays, so across the full spectrum. However, it is quite interesting to see that at least there must be some difference to their exact origin, because in some neutron stars it was seen that the radio pulse and the gamma ray pulses are not aligned in phase, or as it also is important to say that, that they are not aligned in phase. So this leads me to just say that the exact origin of the magnetospheric emission and the physical processes that go on are still rather unconstrained, or at least are an active field of research. And for that very reason, looking at the distribution of sources showing this emission is quite of interest, as we will see later on. More simple in that regard maybe is also if we consider that this emission is rather focused, those objects can give us pulsations due to the lighthouse effect, because when the neutron stars rotating around this rotational axis, it will appear brighter when we are looking towards the cone of magnetospheric emission, while it will appear fainter when we're looking away from it, as you can see. For example, here for one source in this diagram below. If we track the period evolution of these sources for quite some time, we will also see that it's not that the rotational period of neutron stars does not stay constant. For example, here in the diagram on the right, you can see that if we would assume a linear timing solution, so a constant period for the source, we would after some years the error in our cycle counting would add up quite dramatically, meaning that we need at least the second component in the timing solution, the change in period, to properly describe the timing evolution of the source. This breaking that is therefore often observed in sources can originate from a variety of physical processes. For example, the ongoing particle emission that are accelerated in the field can take away energy. Of course, the fallback disk, if present, could apply torques on the rotation. The internal torques, if matter moves around in the neutron star, changing the angular momentum, or not the angular momentum, but the moment of inertia, can change the overall period that we see at the moment. And of course, maybe most simple model, as we come to in a second, is that the ongoing emission of radiation, if you just a dipole rotating in space, can of course carry away energy. In the later case, this so-called magneto-dipole breaking model, one would expect that the relation between the spin down, so the derivative of the period, and the period amounts to something to p times the power of -1. So if we express this with this 2 minus n here, this will give us a so-called breaking index of n equals 3. And if we measure the period evolution of these sources long enough and constrain the breaking index, that would be, for example, then one way to get insights on the exact, on the properties of these sources. Nevertheless, within the magneto-dipole breaking model, the good thing or the easy thing is that already a simple measurement of the spin properties of the source, namely the period and its change, can give us estimates on the age of the source, on the magnetic field strength, assuming a dipolar magnetic field configuration, of course, and at last at the luminosity. And in this regard, it's also interesting if we have a neutron star where we see that the loss of rotational rotational energy is sufficient to power the whole emission. These objects are usually known as rotation-powered pulsars and are more or less the standard type of neutron star that we are looking at mostly. Coming back to the different emission mechanisms in these objects, the last one that I want to go over here is the so-called thermal radiation originating directly from the surface of such an isolated neutron star. And this is quite interesting because the differently to the magnetospheric emission, the thermal emission is not focused, so it's more radiating more uniform in space. And this, in principle, allows us, as we'll see in a second, to gives less observational bias in a way on the observation of the sources, as we will see in a second. Nevertheless, of course, the first thing to go over is why should we be interested in thermal emission of these objects? Well, in principle, this already could allow us to constrain a bit the equation of state. So, as you can see in this diagram on the left from EROSITA infrared 2016, or just EROSITA infrared 2016, you can see different theoretically derived equation of states. And as you can see, in principle, they can be constrained just by measuring the mass and the radius of the source. And if you would now be able to properly model the emission of the thermal emission of such a neutron star, we could not only infer the properties and the state of the neutron star atmosphere and surface layers, and also the compositions, but in principle also we would be able to measure the radius and mass, and thereby giving constraints on the possible equation of state. A second way to do this is also if we look at the long-term evolution of neutron stars. So as these objects are born quite hot and cool down over time, the rate with which they are cooling heavily depends also on the composition and the state of the matter inside of them. And here, maybe it is quite interesting to note that, if we want to constrain the cooling evolution of neutron stars, we need, of course, a large sample of thermally emitting neutron stars with well-characterized emission properties. Namely, we need to know their thermal state, their distance, and so forth and so on. But this is also at the moment only the case for very few sources. So it would be cool if we could increase the sample to better understand really the thermal and evolution, and thereby also then, yeah, the properties of the neutron matter as a whole. There are quite a few reasons for the fact that the thermally emitting neutron stars are still rather rare. Maybe the simplest one, if we have a look how we expect or how we think that the thermal, that those different emission components evolve over time. And as you can see here in this diagram, in young times, usually the magnetospheric non-thermal part of the emission is much brighter than the thermal emission, while at old ages, then the neutron star has cooled down sufficiently that again, it is quite tricky to pick up emission directly from the surface of the source. In a way, there's only rather short sweet spot in the evolution where thermal emission components originating from the surface, indicated here by this bigger black body, or heated surface regions at the magnetic poles, for example, can be picked up in the X-ray or for UV regime. And yeah, so for that very reason, most often or currently the majority of the known population with thermal emission components is in this intermediate rotation pulsar state. But there's also other observational biases that are maybe more observationally based in the current population. So up to now, we have discovered more than 4,300 isolated neutron stars. However, the majority of them has been discovered from observational campaigns in the radio and in the gamma ray regime. And this is also in a way marked if we just have a look here at these three diagrams, and you just count the number of sources that have radio detections or hard X-ray or gamma ray detections, and compare them to that what is seen in the soft X-rays where the thermal emission would be most prevalent. This of course is this is of course somewhat just an interplay of the efficiency of current pulsar sources to detect new members, as in particular in the radio regime where the magnetospheric emission is very prevalent. The efficiency of detecting new neutron stars has been quite well, and the number is only ever increasing. It will probably be even better now, once the SCAR radio array is starting observing towards the end of the century. However, if you also have a look, and maybe in this regard just at the latency of the figure, due to the fact that that there are some neutron star populations, as we will come to also a bit later in this talk, that are rather tricky to pick up in the radio regime, the full phenomenology of the population in a way only unfolds in the soft X-ray regime. So it would be good if we could improve this, or if we really want to have a proper, a well-made-up population of isolated neutron stars. It is in the X-ray soft X-ray regime where we need to search and to look for members. Finally, and maybe this is now a bit of a historic, historic part of the talk. There's also the fact that the mechanism that keeps the magnetospheric emission running, in a way, ceases to work if the neutron star has spun down too much. And this is this was a problem, but also a big hope in the early 90s, because there at the time was the idea that if there are many, and this is still the majority of the population in the galaxy that we don't know about, but if there are some of them moving around through maybe areas in the interstellar medium where there is a bit more matter to be accreted, they could also shine in the X-ray regime. So when there was an X-ray survey set to be conducted, the so-called eROSITA scale survey, there was the hope that perhaps thousands of old neutron stars that are escaping detection in the radio could be finally found. However, the result of this survey in the end was that only 7 sources were found that initially were thought to maybe belong to this ISM accreting class. However, later on, it was figured out that these sources are moving way too fast for efficient accretion to take place. And instead, these 7 sources, the so-called Magnificent 7, in the reason of this nice Western movie that I can only encourage you to watch, are just, or not just, but are just famous for the very simple fact that they are instead not emitting due to accretion, but probably due to just cooling thermal radiation from their surfaces. And as such, it has really taken quite a long time and megaseconds of observations to really see that maybe that there is not only a terminal emission, but also a non-terminal part. However, for the most part, if you look at the spectra of different isolated neutron stars, the X-ray dim neutron star class is really just remarkable because they're only rather well seen in the soft X-ray regime. At the same time, they're radio quiet because, for some reason, magnetospheric emission seems to not working in these sources. They're all right nearby, which is also an observation effect to some degree, perhaps, because the soft X-ray emission is heavily affected by absorption in the ISM. So the range that, or the distance that we could look with eROSITA at the time was still rather limited. Nevertheless, 7 sources were found, which was a great success at the time. If we compare them to the remainder of the neutron star population, we can see that they are characterized by rather large magnetic field strengths, at least if we account the simplification of the dipolar magnetic field configuration in these sources. And they are located at rather large spin periods also in respect to the bulk of the population of the normal rotation powered pulsars. And finally, one very interesting result is that if we compare the loss of rotational energy, so the spin-down luminosity, to the emission of thermal radiation in the X-rays, we can see that the X-rays seem to be a bit too bright to be solely powered by the loss of angular momentum. And this possibly could hint that there was, at the time, must have been some phase of reheating in these sources, either perhaps due to the decay of the magnetic field or maybe heating from a Four-back disk. So all in all, already the intrinsic properties of the X-rays can tell us a lot about the neutron star phenomenology as a whole, and in principle also to constrain the mechanisms that lead to magnetospheric emission, or by properly modeling the spectra, of course, then also modeling, getting insight on the state and composition of the surface layers and the equation of state. However, what I want to point out, because this is probably more important to my work, is that also population properties are quite remarkable and in a way represent all the shortcomings that we currently have as a whole in the neutron star population. For example, in 2008, Keen and Kramer sat down and estimated the birth rates of different types of isolated neutron stars. And the first thing that I want to make you aware of is that if we compare the dominating populations of pulsars and rotating radio transients to the birth rate of the X-rays seem to be at least on the same level, although, of course, the statistics, given that we only have 7 sources, still rather limited. But at least in the local really local universe, in the vicinity of the sun, the birth rates seem to match rather well. Which in principle could imply that there's a large population of X-rays that still needs to be discovered. Or it could be just a projection because the sun is rather close to OB associations of the gold belt, where many progenitor stars are being formed, so that these sources could be, this is just a good position that we're in a galaxy, so, and they could be overall a bit more rare. There's also a second problem. So as you can see here by this black line and marked by those dashed lines here on top and below, this is an estimate of the galactic core collapse supernova rate, which is more or less the dominant formation channel for neutron stars in general. And one would, of course, expect that the birth rates of the different classes, if we add them all up, which is shown by these black bars here, should in principle match the galactic core collapse supernova rate, which, as you can see, is clearly not the case. So in a way, there seem to be too many isolated neutron stars. And if you want to solve this so-called neutron star birth rate problem, there are, of course, a few things that we can think of. The first might be, okay, maybe we really don't have a good idea about the formation rates of these sources, in particular for populations of rather low numbers like the X-rays or the magnetars. That is definitely a problem that needs to be addressed. However, now, meanwhile, with more than 4,000 neutron stars now, this is, I guess, at least for other populations, not that much of a problem. So the second way out would be not to see that those sources are distinct types of neutron stars, but in principle, they are all related to each other in some way or another. And to show this here, for example, on the right, you can see the results of a magnetothermal evolutionary model, or that was calculated, showing the spin property evolutions over time accounting for the effect of magnetic field decay. I want to note at this point that similarly evolutionary tracks can also be obtained if you, for example, assume the presence of a fallback disk. But yeah, this is just an example to show that in this regard, you would expect that if a neutron star would not be breaking and not slowing down over time, it should follow here those dashed lines and be constant along the same magnetic field string. If we now account that the magnetic field may change or the rotational evolution may be affected by other ways like a fallback disk, we then can see that in a way the evolutionary tracks can diverge from those linear tracks. And at least in the magnetothermal evolution scenario, that would mean that the extents in principle could be related to high B pulsars or the magnetar population. However, again, the problem is if we want to probe and to confirm evolutionary connections, this is all a bit tricky if only 7 sources are known. So there is a rather big need already in the extents class alone that the population must be increased. So getting more towards the topic of the talk, the quest is, of course, to find additional members. And maybe the most obvious part or the most obvious place to start looking for them is where we already found some. So it could be, of course, that there might be more sources hiding still in eROSITA. And this is definitely a search that is still very much ongoing. So it's also with quite some success. For example, in 2008, Rutledge et al. Combined Swift observations with eROSITA observations to get better positions to search for possible neutron stars and thereby finding a source that was named Calvera. Also a reminiscence of the Magnificent Seven movie, because that was the evil guy in there. And in a way, this source also kept up to the naming because then it turned out that this is probably not an extents, which might be seen as a bit of an evil thing, but it's in itself also a quite interesting source because this is very high above the galactic plane. And it was, or is still to some degree discussed if it could be a rotation-powered pulsar or maybe not an evolved member of another neutron star cluster, so-called central compact objects. More recently, De Masi et al. Combined deep imaging observations from SDSS, again with eROSITA, and they came up with 55 currently still unconfirmed ionized neutron star candidates. But I think, at least at the moment, there's an XMM-Newton program going on following up some of them. So it might be that soon more members could be identified and will be known. Nevertheless, if we want to use eROSITA, the biggest obstacle has always been, and probably will always be, the rather limited positional accuracy. I mean, at the time, of course, rather superior, but still, if we want to look for neutron stars and they are most prominent in the galactic planes, there is definitely significant source confusion to really confirm the selected candidates and, of course, in the first place, to select possible sources. At the same time, also, it's not super deep, complete only to above 10 to the minus 12. Of course, there are detections that go a bit lower, but overall, it is still rather shallow. So it would be good, of course, to also go more out in X-rays, to go to deeper X-ray limits, and therefore also proper bigger volume in comparison as is possible so far with eROSITA alone. And as such, what we really would need or would like to have, if we would like to increase the sample of thermally emitting neutron stars in general, we need a deeper X-ray surveys with rather good positional accuracy. And I'm pretty sure it's really cool, at least, that we are now at a place where there's really a big leap in that direction possible, because there are now at least 2 catalogs that can be really used for nice neutron star searches. The first one is the so-called eROSITA all-scale survey, and you can see here the eROSITA satellite in small. eROSITA is a soft X-ray instrument observing between 0.2 and 5 keV that scanned the whole sky between December 2019 and February 2022 for 4 to 5 times. And as we are part of the German eROSITA consortium, that was a Russian and German collaboration, we have access to the Western galactic hemisphere only because the idea was, or the collaboration agreed to split the data rights, which means that if we want to search in this catalog, we can only constrain ourselves to the right side here. Nevertheless, we can get a bit deeper than eROSITA. So, so far we have searched for neutron stars above 10 to the minus 13 ergs per second centimeter squared at soft X-ray energies, where already past population synthesis models have predicted that there might be about 20 to 25 extents all sky, but still a much larger number detectable than is currently known. The nice thing about the all-sky survey is that it is in principle not limited by the field of view, so you're observing the whole sky. And this is really cool because at least an observation bias based on the observational footprint of the survey is not directly inherent. And that makes it, in principle, also possible to build complete populations. Of course, this is, of course, tricky. But a complete population would be really nice if we would constrain really the population properties like evolutionary pathways or how the different properties of extents or other Newton classes really are related to each other and are distributed. A second way, the social Newton stars is also possible with the XMM-Newton serendipitous source catalogs. This is just a culmination of all the pointed observations XMM-Newton has conducted since it started its pointing observation phase in, I think, February 2000. And up to now, I think, or probably now already, about 14,000 pointed observations have been conducted. And the idea is here that maybe in the field of view of a target that was observed by XMM, there could just be, by chance, be a neutron star in there to be discovered. As XMM is observing the fields much longer than eROSITA was, it also gets much deeper. So in this search, we went to X-ray flux limits of about 10 times minus 14 ergs per second per centimeter squared. And at the same time, also, we have a rather good astrometry because XMM-Newton is not per se a survey mission, but has therefore a much smaller PSF, which allows a better positioning, which makes it easy to select targets. And as we are here going deeper, in principle, we can probe the more remote ISO Newton star population. However, of course, it is a bit tricky to build complete samples in a sense because only parts of the sky have been observed. Yeah. However, if we now have our X-ray catalog and we want to figure out the Newton stars, we need to have a selection system in place some way or another. And this is really very much like finding a needle in the haystack because the majority of X-ray sources that are discovered are not neutron stars, but AGN. And at least in the eROSITA and XMM-Newton above our flux ranges, we have about 70 to 100,000 input sources that enter the search that we then need to sweep out to find a few neutron stars that that might have been detected. And to do this, we apply in principle two major criteria. The first is, if you think back to the extents, their emission is very much well described by a simple blackbody continua and is also overall steady, at least in flux, so did not change much. So in the first way, we just looked for all the sources which in eROSITA or in repeated XMM observations did not show any significant flux changes and have in a region in hardness ratio space where we would expect blackbody emitters to be located at. And you can see this here in the diagram on the right. Those curves here show for a set temperature, but varying ISM absorption, the location where we would expect neutron stars to, or where we would expect those blackbodies to end up. And then we just select everything, which is this black line, below this black line here, to as a possible candidate, which really is already a good way to remove at least a large part of all the input sources. The second step is then a bit more tricky because that makes use of the intrinsic property that extents have been observed to have large X-ray to optical flux ratios, which means they are much brighter in the X-ray regime than they are in the optical. And this is really one property that distinguishes them from all the other soft X-ray emitting sources that you might find, at least in large quantities, in these catalogs like AGN or CVs or coronal emitters, as you can see in the diagram on the right. As such, if we consider the X-ray flux phase that we are probing here with XMM and eROSITA, we would expect that the optical counterparts of a neutron star are too faint to be detectable to most wide area photometric surveys. As such, one can in principle easily select neutron star candidates by cross-matching all the soft surveys from the previous criterion against these wide area surveys like Gaia, N-stars, or the Legacy survey, and only keep those X-ray sources which seem to lack any optical infrared counterparts. However, this is really where then the problems of the accuracy and the X-ray sky position really play in, because if we want to do the cross match, of course, we need we need in principle a really good understanding of the X-ray sky position to really make sure that it is not erroneous, that the source is not erroneously matched away, or is properly assigned its counterpart. And this is really where, for example, social rosas are really tricky because the X-ray errors are just too large. At the same time, of course, we also need the comparison catalogs in the optical infrared to be deep enough to bring us out of this regime where where AGN and CVs are located at. So this is a second limitation that we have to deal with in this search. Nevertheless, if we just apply these cuts and search for this to the eROS catalog first, we have come up with a first candidate sample of 33 candidates that was published last year in summer. And the sample consists in principle, or can be divided into two parts. Again, there are 13 rather soft sources which are well fit by simple black bodies with effective temperatures below 150 electron volts, which is very much neutron star light. And then there are 20 harder sources, which you can also fit usually well with black body, otherwise they would not have been selected. But in principle, you could also fit in power like model with a spectral index of 1 to 4, which could also be reminiscent of neutron stars, which are predominantly magnetospherically emitting, but also of contaminant natures like an cataclysmic variable or an AGN. And as such, the sources, why they might be very interesting, because the hotter temperature could point to them to be younger and could therefore be maybe important steps to constrain magnetothermal evolution of these sources. It is, however, tricky to say if they're really neutron stars per se, just on the spectral characterization that we can do on eROSITA alone. It is also interesting to note the distribution of these different samples. Again, neutron stars would be expected to be mostly in the plane, or at least neutron stars that we can discover in X-ray energies, because they have not so much time to travel out of the plane, and they should be formed predominantly in there. And again, we can see that the soft sources are mostly actually constrained to the plane. However, the harder ones are distributed all over the place, which might also be, on first glance, not a good result. What is also important to note is that while eROSITA is definitely a better positional accuracy as ROSAT, there's still very much a lot of source confusion going on in the galactic plane, and this can be made a bit better visible if we have just a look at the distribution of the overall candidate sample in galactic latitude in respect to the synthetic population that was calculated by Adriana Pires in 2017. And you can see while the synthetic population really peaks within 5 degrees of the galactic plane, our sample is lacking a few sources there. They are probably being matched away so far, and then only recovers and actually overpredicts the prediction, or exceeds the prediction at higher latitudes. But this is very much something that we are working on. So there is another PhD student now in our group, Deep Chef, who is just now working on improving the selection and the detection of neutron stars in eROSITA to hopefully really push towards the plane and to also find those sources that we've missed so far. If we are a bit brave and we start to, we can, however, still already look how successful this search might have been. And if we are brave enough to do the small number statistics based on the predictions that we got from Adriana's paper, I might already expect that 1 to 3 new instances may be located within those sample of 33 sources. So it is definitely something that we should explore further, and is in a way already a big result. Coming to the second selection of candidates from XMM-Newton, and this is work that is led by Adriana Pires. You can see her image up here. So far, she has selected 11 candidates using similar cuts as we did with eROSITA. And here, again, a bit more than half of those are close to the plane. They are overall soft emitters. Here you can, for example, see the comparison between the eROSITA in gray and the XMM-Newton sample, and they're all below 200 electron volts if we fit their spectra with a simple black body, which in itself also works quite well. And as is also expected, as we're going to deeper flux limits in XMM-Newton, they complement the eROSITA search really well, because it extends the candidate sample to much lower flux values, at least by 1 decade. And if we put all of this together, our current samples are currently is currently comprised of 44 isolated Newton star candidates that we can have a deeper look at now. As I said, there are quite a few limits to the selection. So, of course, it was mentioned already, the depth of the optical infrared comparison with the logs is important to bring us out of the bulk of the contaminant clouds in here. And as you can see, unfortunately, for most of the cases we selected, the current lower limits on the X-ray to optical flux ratios are still too shallow to really significantly confirm their Newton star nature, as they're still very much within this cloud here. So what we need is deeper optical observations to really push those limits more up to rays that can only be reached by compact objects. However, then we run into the second problem again, that also here source confusion can play a role. For example, what you see here is in green an eROSITA position of a possible candidate, but in a much deeper optical image that we got from the VLT. And if you would not have any better X-ray position, you might now start to thinking if this is really a Newton star or not, because in principle you could assign the source or you could measure it away to one of those optical sources in the near vicinity. So we need better positions. And at last, of course, eROSITA, but also some degree XMM, if we go really to the flux limit, not giving us too many photons. So of course you can always fit a nice black body, as you see here, which fits rather well, and you can get estimates on temperature and radius by that. But it would of course be good to have more X-ray photons to better characterize the emission of the source overall, to see if there's maybe also a second black body needed or magnetospheric emission going on in the source. And of course we need many more photons to really search for pulsations, which would really be the giveaway. That is, we are looking here at the Newton star and to place the source within the galactic population. So what we really need is, once we've selected the sources, is to conduct follow-up observations. And this is also in full swing and is still ongoing because we've initiated follow-up at X-ray energies with XMM, NISA, and Chandra, targeting, of course, the spectrum, get better positions to really ensure that we're looking at the Newton star here, or to see weep out remaining contaminants. And of course, to start looking for pulsations. In the optical, we use 8-meter large telescopes like the LBT, SALT, and the VLT to improve the X-ray to optical flux ratio, again, to confirm the Newton star nature. And thanks to Adriana's connections in China now, very recently we are also able to do a follow-up observation for FAST, at least for all targets which are in the northern hemisphere. To look also for pulsations and therefore for the remnants or for magnetospheric emission in these sources. It's also really nice that many of those observations have already been conducted. For example, in AO22 we got a large XMM-Newton VLT program for 7 sources that is fully observed. Meanwhile, Adriana has a rather successful XMM full-fill program ongoing that already targeted 5 sources to improve their XMM-Newton positions. And we have many Chandra snapshot observations and deep imaging with LBT and VLT. And just to give you an idea that really there is a lot to be explored right now, here are many finding charts in blue showing the original eROSITA positions, in green and small, if you can see, better positions from X-rays. And as you can see, many of these targets here can now be really classified based on this follow-up alone. For example, either showing here in this place that 2 bright optical sources merge into one eROSITA source, because the eROSITA PSF is also rather large in that regard, or really confirming Newton star nature as in this case, where you see that there's really nothing and a more improved X-ray pointing from Chandra. We can all put this into numbers now to see and to characterize the state of the follow-up efforts. And again, here you see on the left an X-ray to optical flux ratio diagram, now with updated optical limits from our follow-up efforts. And you see that there are now, meanwhile, quite a few sources which are really at rather large values. And overall, 61% of our candidates have at least one follow-up observations, and a bit more than half, I think 55% of them, are now follow-ups far enough that we really know if this is a possible Newton star or not. And these numbers you can see here in the table, showing that at least in the soft sample of the eROSITA selection, there seems to be really a high success rate, that already at least there must be 9 compact objects if we trust the X-ray to optical flux ratio value alone, and only 1 contaminant so far. The hard sample, on the other hand, as might have been already predicted, by just looking at the galactic distribution of these sources and the fact that they, in principle, their spectra could, or well, at least also in agreement with contaminant natures, have so far turned out to be no neutron stars. However, yeah, we will keep on looking, and maybe there's one rather hotter one that would be really cool to see. And with XMM at last, this is an effort. This is, yeah, I would not say just starting, but we are still waiting for lots of follow-up observations in the optical to be conducted in the near future, so that even more than the 2 confirmed compact objects so far will be hopefully found to increase these numbers overall. Nevertheless, I think it's already quite a success that not even having the full Kanye sample being followed up, the search has already unveiled 11 very likely neutron stars that can now be followed up in more detail. And in this regard, there are 2 sources which are really, yeah, remarkable, because this is where we learned most about so far, and where a lot of this follow-up effort has gone into. These sources are eROS UJ0657 and eROS UJ1317. You can see here the initial optical follow-up of the LBT and SALT going to R-band magnitudes of about 25 meg, 25 meg, and the initial eROSITA spectra, which are overall well fit with a black body. If we keep with the first source for the moment, this was also part then of our XMM-Newton and VLT large program, but we also were able to obtain another nicer observation and even 5 hours of fast follow-up to look for positions in the source. And you can see here on the left, again, a much deeper finding chart, showcasing the original eROSITA position in blue, the green updated X-ray position from XMM-Newton, showing here the 1 sigma error ranges, and some optical sources in the field of view. And the first thing is to note, based on XMM at least, the source cannot be associated to anything in the optical here, which implies, given the magnitude limit of 27.3 in these observations, that we must be looking at a source with an X-ray to optical flux ratio lower limit of at least 5,000, which is very much of an order that is reached by isolated neutron stars only, or by and maybe some X-ray binaries. But this already is quite a nice result. The spectrum is also really interesting because it is of predominantly thermal nature and best fitted by 2 black bodies combined with 1 absorption feature at low energies. You can see this here in the residuals somewhat, that a 2 black body model alone doesn't cut it completely, but if you add a feature here at lower energies, then you get a much better fit again if you compare the chi-squares. And this is also an interesting result because, at least from the X-rays alone, the source seems to be also of predominantly thermal nature, like the X-tons. And yeah, the best result, or the most important result, however, for the source was that both the XMM-Newton and the NICER follow-up showed pulsation. And here we're looking at a period of about 261 milliseconds. And given that those observations were close enough in time to connect them, not in phase, but at least to get a nice estimate on the spin down already, we look here at a source, which if we put it in a spin period versus spin down diagram, would be located at a place where the rotation powered pulsars are most prominent. Such a rotation powered pulsar nature is also supported by the very fact that the X-ray luminosity is about 2 orders of magnitude below the loss of angular momentum in the source, at least based on our current timing results. So this all seems to shake out. However, the interesting spin in this target is really that not only in X-rays we don't see any magnetospheric emission, but also the 5-hour fast observations has not unveiled any pulsations in the radio, nor has a search in the Fermi data at the position of the source shown anything that could be associated to this object. As such, it looks like we're looking here at a rotation-powered pulsar that is, however, quite in the radio and gamma ray regime, which showcases the power of X-ray searches in general to find sources that would at least be missed in conventional pulsar searches as they would be conducted in the radio and the gamma ray. So while this is not an X-ray perhaps, this is also still a really cool result and important to really complement the population of isolated neutron stars. The second source, eROS UJ1317, was also part of the XMM-Newton and VLT large program. Again, we got more nicer observations, and you see again the same diagrams here. So we have a deep optical finding chart, blue eROSITA, green XMM-Newton. The source cannot be associated again to anything in the optical, giving us, in this case, an X-ray optical flux ratio of about 10,000, which is now really the level which I think is almost the same as in some of the non-magnificent 7. I think J0420 has a similarly large X-ray optical flux ratio. Again, the spectrum the continuum is radar thermal, fitted by a single black body. However, now we need 2 absorption features to get a good fit. And if we assume these absorption features to originate due to proton cyclotron resonances, for example, or they would indicate a magnetic field of about 5 times 10 to the power 13 Gauss, which would be in a similar region as what would be expected in a magnetodipole model for the other extents. So this looks, at least in this regard, like a high magnetic field pulsar. At last, we also found the spin, or the period for the source, here in giving us a nice double hump profile here, at a period of about 13 seconds, so also long period like the extents. However, the initial nice-line XMM-Newton observations alone were not able to give us a nice estimate on the spin down initially. So these results were published in 2024, but it is clear if we want to confirm the nature, we need to also measure the spin down to replace them in the spin versus spin down diagram, the source, and we did so. So we got another 120 kiloseconds of NICER last year between March and June. The source was observed repeatedly and allowing us now to really get an estimate on the spin down of about 10 to the minus 13 seconds per second. And if you put this again in such a diagram, comparing the spin down luminosity, so the loss of rotation energy, to X-ray luminosity, we see here indicated by this gray region that the source seems to is not only in a region where the X-rays are located, but also seems to emit more in the X-rays than it could be if it would solely be powered by angular momentum loss. And this is quite interesting because in principle that could again then imply that the source in its past evolution might have undergone a phase of reheating. It's also indicative that the source is located right where the extents are in this diagram. So what we're looking here is very likely a highly magnetized neutron star that is very similar to the extents, in particular, or maybe the first extents discovery in that regard in more than 2 decades. And we're currently writing this up to be published rather soon. So this is also a really nice result. Of course, you also probably ask yourself, what about the other sources, if I go into detail of those too. They're also very much interesting. For example, here you see 4 sources which are part of a paper that has just been accepted 2 weeks ago and will appear on arXiv really soon. These are also similar like the other sources, well fit by single black body models with temperatures between 15 and 18 electron volts, very reminiscing of isolated neutron stars that are thermally emitting. And 2 sources we have also similar absorption features like in J1317, implying if we subscribe to the cyclotron, proton cyclotron resonance rational, a magnetic field of 10 to the power 13 to 10 to the power 13 Gauss. But also here it is the case that we don't see any high energy excess, although the limits that we get from XMM-Newton alone on this high energy excess are not deep enough to really exclude its presence. Unfortunately, though, timing searches in these sources have so far been in vain, which is more or less the case for all the targets that we have so far. So there are definitely more X-ray follow-up is needed yet. Nevertheless, it is quite interesting to note that at least 2 of them, J0840 and J0819, are northern enough that we could at least follow them up with the fast radio telescope. And you can see here in the diagram on the right in blue the cumulative distribution of the radioluminosity of all the pulsars currently listed in the 18F pulsar catalog. And in red, we show the limit on the radio emission for J0840 and in green for J0819. And you can see that we already, with the fast observations, very much are at the lower limit of this local population of 18F pulsars. which at least implies a rather radio-quiet nature, similar to that we observe in the X-rays, for example. So I want to leave you here in this talk with the with the takeaway message, so to say, that with eROSITA and XMM-Newton, we are not only increasing the population of isolated Newton stars, but also of rather elusive sources that at least would be overlooked in most conventional pulsar searches. And this brings me to my summary and conclusion slide. So yeah, thermal-limiting isolated stars allow for unique insights into new star properties and evolution. X-ray surveys are very important to complement the population, with us having discovered so far 44 candidates. Hopefully this number will increase even more in the near future. And about 55% of the candidate sample is explored so far that we know if it is a Newton star or likely Newton star or not. And we really start now to see rather rare Newton star classes that are usually overlooked. And at least 9 more Newton stars have been discovered that are currently being classified. And this just leaves me with the very much ending message that this is a story that is definitely still to be continued. And I hope in a year or two from now, we will have even more of these elusive but very cool Newton stars to look at. Thank you for your attention.
Thank you very much. It was a very nice talk. I was going to ask you if there are any questions, but there is one already from Sergei Popov. I don't know if you can see from the chat, but maybe I can read as well. There's a comment on to slide 18. Harder sources potentially can be accreting isolated neutron stars, accretion onto polar caps. Do you consider in parallel this possibility?
Yes, this is definitely a possibility that needs to be considered. And well, maybe this brings me to another slide if you if you have a bit more time. So those harder sources are definitely interesting and they need to be classified. I mean, most of them can be explained rather well already, because if it's a blend of two optically bright sources, for example, in some cases this is just stars that have also a soft X-ray emission together that can be done, however, explained as well. However, there are also contaminants in there that are quite intriguing, and this is also a source of the paper that is said to be appearing next week on arXiv probably. That is J1445 which has an optical counterpart at 24.5 magnitudes, an overall thermal spectrum which is fitted by a single black body of 210 electron volts more or less perfectly, as you can see from the chi-square here. What is a bit tricky is that we did not see any significant pulsations in the source yet, nor do we see any strong modulation in its long-term X-ray flux, at least as far as it's covered with eROSITA and XMM so far. But what I want to say is, while this set of observation data does not really allow yet to really constrain the nature, in principle, it could be also a really extreme AGN with a rather strong soft excess and really steep power law. What might be more likely if this is really a galactic source, at least based on the small emission region, which is about 300 meter per kiloparsec distance in this source, that looks at least like a pulsar cap that could be, have been heated in the past. And in that case, like you said, Sergei, it could be thereby a neutron star in a binary system. So even if I now maybe was not too optimistic, given that it is a contaminant, so it's not an isolated neutron star, it is definitely a case that these contaminant sources that we are discovering are of themselves quite interesting to study, and definitely could be accreting neutron stars, like X-ray binaries.
All right. No, thank you very much. I had another question, quick question. Did you have any estimate on the distances of these newly discovered ones, at least from, black body fits and stuff?
Yes, I mean, distances is always a bit tricky. But if we use the NH that we have from the fit, so the hydrogen column density, and compare it to the extinction cube from Doroshenko et al. That was published last year, the upper limits on the H usually constrain distances up to 1 to 2 kiloparsecs. So at least in that regard, that looks rather local. Yeah, I think for one of these sources, the really soft one, J0819, the NH is even much lower, so this really looks like a nearby source. But it looks, at least from those fits, that we are really looking at a local population, as you would also expect, because again, the ISM absorption limits in a way the volume that we can probe with X-ray surveys at the moment.
All right, thanks a lot. There is one more question here. They say, what is the optical data used for your FX over F optical criteria?
In the search or now, meanwhile, in the follow-up results?
Uh, AJ, do you know which one?
Yeah, I mean, I can just say both. So,
Search, apparently. Yeah.
so in just the candidate selection, we looked at everything that is available, namely the legacy survey, Pan-STARRS, Gaia, whatever is there. Although, of course, Gaia is rather shallow in regard to the other two. Now, of course, in the near future, if there are deeper surveys like the legacy survey of space and time becoming available, this will be even better because they, again, will be much deeper, allowing already much tighter constraints. But that was what we had at the time last year when we did those initial searches. Afterwards, really, then we went to the LBT and VLT to really get deep imaging with exposures of 40 minutes to an hour of the field of view. And there really we then get to deep limits between 26.5 and 27.5 magnitudes in some cases. So so we're getting really deep.
Yeah, that's really deep. All right, thank you very much. Are there any other questions? Either from the chat or none? One very small question from me. You mentioned about Gaussian absorption lines, absorption line-like features. Was there any harmonic nature in those? Because I noticed in several cases there were two Gaussian lines. Was it,
Yeah.
what are the energies? How well can you constrain those energies?
So in the first source, the rotation pulsar, there's only a single line. However, I would say if you perhaps have a better X-ray spectrum with future observatories like Athena, maybe that might be possible, then you might start seeing more. But in this case, it was only a single line. However, for this X-TINs here, there are two, and the one is at 350 electron volts, I think, and the second at 590. So you can, yeah, okay, it's a bit tricky to be seen here, but about here and about here. And that could be roughly a 1 to 2. However, I would be careful in that regard. I think I read once in a paper that higher orders of at least cyclotron resonances could be highly suppressed. So it needs to be seen. And I think it was also the case for the other X-TINs that in some sources there was the idea that they could have harmonically spaced lines. But I think also in the end that was never really confirmed if this is really harmonically spaced cyclotron resonances or if the lines may not be occurring due to different mechanisms like absorption and electronic transitions in the atmospheric layers of the star and so forth and so on. So yeah, we have lines, we can interpret them in a way, but I would say more data is always better to really target the nature.
Thank you
Maybe
very
in
much.
this, yeah.
Perfect. Any other questions? One last chance. All right then. Okay, thank you very much, Jan, one more time. It was great to have you here, listen to your talk, and thanks a lot.
Yeah, thank you for the invitation and the opportunity.
Thank you for the talk. Yeah.